Stupid ice. It's a shame that ice floats. It makes it hard to drink. If only ice sank.
Ah, but if the ice sank, it would take a lot longer to cool your drink.
Why is that? The ice is cold, the drink is warm. Nature will balance them out.
Yes, but only through conduction. When the ice floats, convection creates a circulation to cool the drink a lot faster.
Convection. What's that?
I'll show you. The water that's closest to the ice cools down first, by conduction. When the water cools, it becomes heavier and sinks. As it sinks, the warmer water below comes in to replace the sinking water. This is what convection looks like, and this circulation is what helps cool the drink quicker.
How so?
It helps to move warmer water closer to the ice. Conduction transfers the thermal energy from the water to the ice more efficiently the warmer the water is.
Okay, so what's conduction?
It's the transfer of thermal energy between neighboring molecules due to a difference in temperature. For example, suppose you had a warm mug and you set it down on the table. What happens to the tabletop under the mug?
It gets warmer.
Right, it gets warmer, because the mug is in contact with the tabletop, and the mug is warmer than the table. Now the same thing happens with the water around the ice. The thing to note here is that this transfer of thermal energy doesn't require any mass to move around. But let's get back to the floating ice and the sinking ice. I'll now demonstrate how much of a difference there is between cooling due to only conduction and cooling due to conduction with convection.
You carry around beakers of water?
Behold! These beakers contain water at room temperature. I suppose we'd want to cool them off. We'd need ourselves some ice, no?
Sure.
But to do this right, we need some floating ice and some sinking ice. Now, let's see. Wait.
Yes, sir.
Yes, could we get a couple blocks of colored ice, margarine dish size, one with a bit of chain in it?
I'll see what the kitchen can whip up, sir. Here you are, sir.
Thank you, that's all for now. Okay, so we've got our ice and we've got our water. Let's throw the ice in and see what happens.
Hey, what's going on here?
We're demonstrating the redistribution of thermal energy through convective mixing and comparing it with purely diffusive means.
Of course we are. How did I miss that?
So in this beaker, the colder water near the ice is already at the bottom. It can't sink anymore. So the colder water stays at the bottom and the warmer water stays up at the top.
I see dye sinking on the right. I bet that will make the ice melt faster.
Let's speed up the action and see.
Whoa, all the floating ice is gone, but the sunken ice is barely melted.
Yeah, so not only has the floating ice melted faster, but check out what happened with the dye. The dye is in all of the water for the floating ice experiment, whereas all the dye is stuck at the bottom in the sunken ice case.
That's because in the beaker with the floating ice, the convection created a circulation to mix the water. While in the beaker with the sunken ice, there was no movement of water.
Yes, that's right. The same thing is true with the temperature. If you notice, the further down you go in the sunken ice case, there's a large change in temperature. It gets warmer and then it's cooler on the bottom. Whereas for the floating ice experiment, it's uniform throughout.
So if I were to use a straw, the sunken ice wouldn't actually be so bad, would it?
I suppose not.
And if we were to stir the drink, the whole thing would get cold, right?
I prefer mine shaken, not stirred.
Well, where else do we see convection?